Let's start question number 11 now. A carpet of mass m made of inextensible material is rolled along its length in the form of a cylinder of radius r and is kept on a rough floor. The carpet starts unrolling without sliding on the floor when a negligibly small push is given to it. Calculate the horizontal velocity of the axis of the cylindrical part of the carpet when its radius reduces to r by 2.
So now here in this problem, we don't know anything, like no forces, no torque, anything. Let's sketch the problem first. So here we see that we have been given an initial condition where a carpet is kept and its radius is say r, and now it has started to unroll over here. We have given a small push. Now as time proceeds, this will unroll and the carpet will go, it will unroll and form something like this. And now in the final situation it says that now it has reduced to r by 2. Okay?
Right.
So now here we are not sure of any of the forces which are acting on this carpet except for the gravitational force, since there is no other external force, and since it's rolling there is no motion of point of contact, and therefore there is no friction in this situation. Right? Now since we don't know any forces, we can't find any acceleration or anything like that. Right? So now, but we need to find the velocity over here. So what we'll do is we'll use the energy concept over here. How? Now we can see as the carpet will unroll, its center of mass will start dropping. As the carpet unrolls, it will become smaller, and since now here it has reduced to r by 2, the height of center of mass over here becomes r by 2, whereas initially it was r. So we see that the height of center of mass is falling. So as the potential energy is lost, some kinetic energy is gained, since there is no work done on the carpet anywhere. Right?
True.
So now here we find out the initial potential energy of the carpet to be mg into r, right? Where m is the mass of the carpet. Simple. Initial potential energy. Let's write it down as potential energy initial, right? The final potential energy will be final will be equal to mg into r by 2, right? No, there's a catch over here. You see, I've used the same mass over here, whereas when the carpet unrolls, some of the mass gets laid on the ground.
So
it's not the complete mass over here. So this is wrong. What we need to do is we need to find out the final mass, the mass which is at this height, concentrated at this height r by 2, right? So now for that, what do is we can say that the mass is uniformly distributed throughout the carpet, right?
So it should be m by 2?
No, again wrong. You see this area, you can see from the side angle, right? So the mass will be uniformly distributed throughout this area, right? So let's take mass per unit area as we can see it from here.
Okay.
Right? So mass per unit area will be m by pi r square, right?
Right.
Now the final mass will be this mass per unit area into pi r by 2 square.
Okay, right.
So this will give me final mass as m by 4.
Okay.
Right? So it's not m by 2, it's m by 4. This is the important catch which you need to understand over here in this problem. Right? So now the final potential energy which we find out. Potential energy final. This will be equal to m by 4 into g into r by 2. Right? So now this loss in the potential energy will be equal to the gain in the kinetic energy. Right? So to find out the gain in kinetic energy, since the initial kinetic energy is 0, the gain in kinetic energy will be equal to the final kinetic energy. So this final kinetic energy will be given to us by potential energy initial minus potential energy final. Right? So putting the values in, we get 7 mgr by 8. Right? This is mgr minus mgr by 8, which will give me 7 mgr by 8. Right?
True.
So now I know the final kinetic energy. Now what I need is the velocity. Right? So for that, now I need to understand what this kinetic energy final consists of. Now since the carpet is rolling and also moving ahead at the same time, there will be translational as well as rotational kinetic energy involved over here. So let's write down the expression. So 7 mgr by 8 will be equal to half into now the mass of the moving part, which is m by 4, right? M by 4 into v square, which is the mass of the center of mass, velocity of the center of mass, I'm sorry,
Yeah.
plus half into I into omega square. Again, the I will be the moment of inertia only of the part which is rolling. Right?
Right.
Now we know that this rolling part of the carpet looks like a cylinder. It's a solid cylinder basically.
Yeah, it's
Right? So we know that I of a solid cylinder is given by half mr square. Right? So we'll put in those values. So the final expression will become 7 mgr by 8 equal to half m by 4 into v square. Here this v is the one which has been asked in the question. They want us to give the final velocity, right? So this plus half into I will be again half into m by 4 into r by 2 square. I hope you are getting here. M by 4 is the final mass and r by 2 is the final radius of the cylinder which we are considering, and into omega. Now since the carpet is rolling, omega has to be equal to v by r.
Yeah,
Right?
yeah, right.
And as it is, we are not interested in omega, we are interested in v. So we'll write this down as v by r by 2.
Right.
Right? R by 2 square.
So this is the final
Final expression.
energy.
We know everything over here. We know the r, we know m, we know g, we know everything. The only unknown in this expression is v. So when
Velocity.
we solve this expression for v, we find out that v is equal to under root 14 g r by 3. This is the required answer.
Right. So in this question, we started with very few given variables to
Right.
us. So and we saw the combination of translational and rotational motion.
Right.
The important point to note in this question is the mass distribution per unit area, right?
Right.
Because the mass is variable, the mass is changing.
Right.
So you need to be careful, and we assumed the mass per unit area to be constant for the carpet.
Right.
Right? That is question number 11. Here comes question number 12. A homogeneous rod AB of length L is equals to 1.8 meters and mass M is pivoted at the center O in such a way that it can rotate freely in a vertical plane. The rod is initially in the horizontal position and in sect S, this is the given figure, and in sect S of the same mass M falls vertically with speed v on the point C midway between the points O and B. Immediately after falling, the insect moves towards the end B such that the rod rotates with a constant angular velocity omega. Part A. Determine the angular velocity omega in terms of v and L. Part B. If the insect reaches the end B when the rod has turned through an angle of 90 degrees, determine v.
So here in this question, we see that an insect is falling on a rod which has been hinged at its center. The initial angular velocity omega can be easily found out using the concept of the conservation of angular momentum, since it's the basic thing to happen, right? The angular momentum has to be conserved since there is no external forces around here. Now, once the rod starts moving, there is an external torque provided by the gravitational force.
Yeah.
The gravitational force acts on the rod at its center of mass, which does not give any torque. However, the gravitational force acting on the insect is not at the center of the rod where it is hinged. So that will obviously give a torque, right? So now we move on to find out the angular velocity first and complete with the part A of the question. Part A. So over here we see that the initial angular momentum will be mv into L by 4. L by 4 is the distance of the insect falling on the rod, right? So mv into L by 4, this should be equal to the final moment of inertia of the system, that is the rod plus the insect, into the omega, right? So the moment of inertia of the system, the rod plus the insect, will be given to us by ml square by 12 plus m into L by 4 square. This, and now since we need the angular momentum, we multiply this by omega, right? Now here we know m, we know L, and we need to find the initial omega in terms of v. So solving this linear equation, we can easily find omega. Omega will come out to be 12 by 7 into v by L. Right? So
Right.
part A is very simple over here. Now moving on to part B. Part B says if the inset reaches the end B when the rod has turned through an angle of 90 degree, determine the initial velocity v. Right? Now here we see that there is an external torque acting, so the angular momentum won't stay constant. Also, since the inset is moving on the outward side, the moment of inertia does not stay constant around here.
So when we consider the entire system, then
Right.
the external forces are zero. The external torque is zero, right?
No, the external torque is still there because the gravitational force is acting on the inside, which is providing the torque. That force is not passing through the center of mass of the rod where it is hinged.
Okay, yeah, right.
So that will give an external torque, and so the angular momentum does not stay constant.
Right.
And also, since the insect is moving, the moment of inertia does not stay constant. So here there are a lot of variables which are changing, you see, with time. So for now, let us assume any time t and find the conditions for that time. Right?
Okay.
So let's start with part B, and let us assume that the insect is at some point over here at a distance of x from the center O. Okay, we assume this distance to be x at some time t.
Okay.
Right? So the total angular momentum at that moment will be the moment of inertia, which will be ml square by 12 plus mx square now.
Right.
This into omega. Right? Let
Yeah.
us take the variable as k. Let k denote the angular momentum at some time t when the insect is at a distance x from the center. Right? Next thing which we know is the torque is acting. Right? Now I am drawing a separate diagram. Let's say now at time t it is somewhere over here. This is point O. The insect is somewhere over here at a distance of x. This is the gravitational force mg. Right? Now to find the torque, we'll have to resolve this mg into this direction perpendicular to the rod and multiply that with x to find the torque. Right? Because the torque is the force into the distance, basically.
Yeah.
Right? So we resolve and we multiply it with x. So that will give me the torque at time t when the insect is at a distance x from the center to be mg cos theta. Let theta be the angle which the rod has already rotated through. Right? So this will give me mg cos theta into x. Right? Now, the most important equation which I pointed out during the introduction. Do we remember that? That dl by dt is equal to tau. Right? Because here everything is changing, we move on to the most important equation.
Yeah.
Right? Now here for L we have used k, the angular momentum, total angular momentum. Right? So for our variables, this equation becomes dk by dt equal to tau. Right?
Right.
So let's move on to put in all the values and let's see what comes ahead. So dk by dt, this will be m L square by 12 plus mx square into d omega by dt plus omega into 0 plus 2mx into dx by dt. Right? This should be equal to tau, which is mg cos theta into x. Right? Now we have been told in the question that the angular velocity omega remains constant. So we see that d omega by dt is 0. Right?
Yeah.
Now writing rest of the equation, we get 2mx omega into dx by dt equal to mg cos theta into x. Right? Now from this equation we see we can get dx equal to g by 2 omega into cos theta into dt. now we see that theta is equal to omega into t. Now we know that at time t equal to 0, now we know that at time t equal to 0, the initial theta was 0 and the initial x value was L by 4. And also we know that at time t equal to t1, let's say the rod becomes vertical at time t1. Okay. So at time t equal to t1, we get theta equal to pi by 2, right? And x...
Theta is the angle with the horizontal.
Right. And x equal to, we get L by 2, right? Let us say this is t0 instead of t1. And let t1 be any random time.
Okay.
Actually we don't need t1 over here. Let's integrate the equation which we had got earlier, which was dx equal to g by 2 omega into cos theta dt. Right? This was the equation which we had got. So when we integrate this, the x goes from L by 4 to L by 2. Just a minute. From L by 4 to L by 2 dx. This goes g by 2 omega is constant into the integral becomes cos of omega t dt, where time goes from 0 to t naught. Right? Now we'll integrate this, but before that, one thing which we need to see over here is that at time t equal to t naught, the angle rotated is theta by the angle rotated is pi by 2, right? And the constant angular velocity was there, which was omega.
Yeah.
Right? So we know omega, we know theta. So can we find t naught? Obviously yes.
Yeah.
Right? So t naught will be equal to theta by omega.
Yeah.
Which will be given by pi by 2 omega. So let's replace the t naught over here with pi by 2 omega. This goes away and we get pi by 2 omega. We have basically just gone out one variable is lesser once we integrate this, right? Our attempt should always be to work with lesser number of variables. Right?
And so in this question already we have a lot of variables.
Right. And too many changing quantities, too much integration and stuff.
Yeah.
So let's move on to lesser variables now. Now when we integrate this, we get L by 4, that is L by 2 minus L by 4 on left hand side. This will give me g by 2 omega into sine of omega t divided by omega, and the limits will be from 0 to pi by 2 omega, and putting in all the limits etc, we'll find out that the value of omega comes out to be under root 2g by L. Fine? Now, however, the question asks us for the initial velocity. So how do we find the initial velocity? Do you remember we had found the expression for omega initially in terms of velocity v as 12 by 7 into v by L, right? So now we'll equate both of them, basically simple as that, under root 2g by L equal to 12 by 7 into v by L, which will give me v equal to 3.5 meters per second after putting in all the values which have been given into the question. And here we have our answer that the initial velocity needs to be 3.5 meters per second.
Right. So this was a pretty lengthy question involving a number of variables, and such questions are very important from competitive exams point of view, right? And in this question we had to deal with a lot of integration and a number of other variables also, like theta, t, and all these things have to be dealt with properly. With practice, you need to make sure that calculation errors avoided.
Here you will see that we have visualized the problem in the initial state. When we saw that the insect was falling and it was moving ahead, we saw that there had to be some differentials, there was change in inertia and everything. And so we went on to use the differential equation to find out the final answer.
Right. So this was question number 12.